All right, let's do this.
Nash embedding theorem, embedding curved spaces in flat ones. The Nash embedding theorem, a profound result in differential geometry established by John Forbes Nash Jr. in the 1950s, states that any Riemannian manifold can be isometrically embedded into a Euclidean space of sufficiently high dimension. In simpler terms, this means that any curved space, regardless of its complexity, can be faithfully represented as a subspace within a higher dimensional flat space, preserving all distance measurements. This theorem bridges the gap between intrinsic and extrinsic geometry. Intrinsic geometry deals with properties within a space itself, such as distances and curvatures measured along paths within the space. Extrinsic geometry, on the other hand, considers how a space sits within a larger ambient space. Nash's theorem demonstrates that the intrinsic geometry of a Riemannian manifold completely determines its extrinsic realization as an isometric submanifold of a Euclidean space. There are two main versions of the theorem, differing in the required smoothness of the embedding. $C$1 continuously differentiable embedding theorem. This version, proven by Nash in 1954, states that a Riemannian manifold can be isometrically embedded in a Euclidean space with a relatively low dimension. While the embedding is continuous and has continuous first derivatives, it can be highly wrinkled and counterintuitive. This is sometimes referred to as the Nash-Kuiper theorem, due to related work by Nicholas Kuiper. $C$K$, K times continuously differentiable, an analytic embedding theorem. This later version, proven by Nash in 1956, deals with smoother embeddings. For $KGE3 are analytic. The required dimension of the Euclidean space is significantly higher than in the $C$1 case, and the proof is considerably more complex, involving the innovative Nash-Moser implicit function theorem. These embeddings are less wrinkled and align more with our intuitive understanding of smooth surfaces. The precise minimum dimension of the Euclidean space required for the embedding depends on the dimension of the manifold and whether it is compact or non-compact, as well as the desired smoothness of the embedding. The initial bounds provided by Nash were quite high, and subsequent work has improved these estimates. Implications of the Nash embedding theorem. The Nash embedding theorem has significant theoretical implications. Unification of geometry. It shows that the study of intrinsic Riemannian geometry can be translated into the study of extrinsic geometry of submanifolds of Euclidean space, providing a powerful tool for understanding curved spaces. Existence proofs. It guarantees the existence of isometric embeddings, even if the explicit construction of such embeddings can be challenging. Foundation for further research. It has spurred significant research in differential geometry and related fields, including the development of techniques like the Nash-Moser iteration. Examples illustrating the concept, though not explicit constructions from the theorem. While the Nash embedding theorem guarantees the existence of isometric embeddings into high-dimensional Euclidean spaces, visualizing these embeddings directly can be difficult due to the high dimensions involved, especially for the smooth case. However, we can consider simpler, lower-dimensional examples to grasp the idea of embedding a curved space into a flat one while preserving distances. The surface of a sphere. A familiar example of a two-dimensional Riemannian manifold is the surface of a sphere. We intrinsically measure distances on the sphere using great circles. The Nash embedding theorem tells us that this curved 2D space can be isometrically embedded in a higher dimensional Euclidean space. We commonly visualize a sphere embedded in 3D Euclidean space, $math BBR cubed $. This is an isometric embedding. Distances measured on the surface of the sphere correspond to the straight line distances in $math BBR cubed $, only if the path in $math BBR cubed $, lies entirely on the surface of the sphere. The theorem guarantees such an embedding exists for any Riemannian metric on a two-sphere into a higher dimensional Euclidean space. A flat torus. A flat torus is a two-dimensional manifold that is intrinsically flat, like a Euclidean plane, but is often visualized as a surface embedded in $math BBR cubed $, with a donut shape. The standard embedding of a torus in $math BBR cubed $, is not isometric. Distances measured on the surface of the embedded torus in $math BBR cubed $, do not correspond to the intrinsic flat distances of the torus, e.g. going around the hole, has a non-zero length in the embedding, but can correspond to a path of zero intrinsic curvature on the flat torus. The Nash embedding theorem implies that a flat torus can be isometrically embedded in a higher dimensional Euclidean space, where its intrinsic flat geometry is preserved. This embedding would not look like the familiar donut in $math BBR $3, the hyperbolic plane. The hyperbolic plane is a two-dimensional space with constant negative curvature. Unlike the sphere, it cannot be isometrically embedded in $math BBR $3. Attempts to do so result in self-intersections or require the surface to be infinitely wrinkled in the $C $1 sense. The Nash embedding theorem guarantees that the hyperbolic plane can be isometrically embedded in a sufficiently high-dimensional Euclidean space. In essence, the Nash embedding theorem is a powerful existence theorem that assures us that the rich and varied landscape of curved Riemannian manifolds can all be found as subspaces within the simpler, flat structure of Euclidean